In this lesson, we're going to focus on derivatives of inverse trigonometric functions. But to start with, what are these things and why do you need them? So here we have a graph of what is known as arctangent, or written tangent inverse of x. One thing to know about this graph is, well, it's the inverse of tangent. Therefore, the domain is all real numbers. So I'll just state that the domain goes from negative infinity to positive infinity. You can plug any number you want into this function, and the range, the numbers that you get back, the smallest y value is negative pi over 2, and the largest is positive pi over 2. You actually never achieve these values, so the range goes from negative pi over 2 to pi over 2. Now, why would you need an equation or a function like this? So here I have a very simple equation. Tangent of x is equal to 5. What is the solution to this equation? How can you figure it out? It's either the case that you just happen to know the answer, or you have to use a function like this to solve for x. Let's just go through that process to check it out. If you want to solve this thing for x, you want to cancel the tangent, and this is where tangent inverse or arctangent comes into play. You can use either of the notations. I guess I'll just stick with the tangent inverse. But what you do is you apply this to both sides of your equation. So we're doing the same thing to the left and the right. So on the left, we have tangent of x, and on the right, we have 5. Because of the way this function is set up with its domain and range, I know tangent inverse of tangent of x. These cancel each other as they're inverses, and you're left with just x. So here I have x. And on the other side, we have tangent inverse of 5, which, of course, you could also write as arctangent of 5. They mean the same thing. I mean, that is your exact answer, either one of those. Of course, I'd rather look at it in a calculator. So here I'm going to my calculator, and it's set currently in radian mode, which is great. And I'll do tangent inverse of 5. And the number I get back, it's approximately equal to, I'll go 2 decimal places, 1.37. That's about what this is equal to. So if I put 1.37 into this equation, you'll get about 5. And the more decimals you add, the more accurate your answer will be. It's also possible to see this solution off of this graph of arctangent as well. So here's what this would look like. Just for reference, pi over 4 and pi over 2 are decimals. I'm going to write those. Well, pi over 4 is about, let me see. Pi over 4 is about 0.79. And pi over 2 is about 1.57. So 1.37, it's roughly somewhere like right about maybe here. So here is 1.37. And if you go to the function, it will take you to 5. So this is what it means by an inverse function. It reverses what tangent does, and that's what it looks like on the graph. Now that we've discussed what inverse trig functions do or where they're used, let's ask a calculus-based question. So in example 1, I want to find the equation of the tangent line to the graph of arctangent at x is equal to 1. So here I have a zoomed in version of arctangent. So it's the same graph as in the previous slide, but we're zooming in on it from -3 to +3. So here's x is equal to 1, and it looks like the y value is pi over 4. What is the equation of this tangent line? To answer this question, what you need to know is, well, if y is arctangent of x, I need to know a formula for the derivative. I'm simply just going to state it here first, just like say what it is. And on the next slide, we'll actually prove where this thing comes from. This is the formula for the derivative. It is 1 over 1 plus x squared. So if you see arctangent and you want to take its derivative, you get this thing here. Now, in terms of finding the equation of this tangent line, well, let's see, maybe I'll use this form of the line. y minus y1 is equal to m times x minus x1. What we need is a point, and I'll use this point here, the point 1 comma pi over 4 for my x and my y. And the slope m is going to be from is going to come from the derivative. So let's start with the slope. Slope at 1 is going to be 1 over 1 plus 1 squared. That's 1 over 2, and actually that's it. That is a half. So that is the slope of this line. Fantastic. Like I said, the point, so you also need an x and a y point, and this is the point 1 comma pi over 4. And you can actually get this from the equation too. You know, the equation is y is equal to arctangent of x. And here if you put 1 into x, it should be that you get pi over 4. And this is true. And if you think of the fact that tangent is an inverse function, or arctangent is an inverse function, this is because tangent of pi over 4 is equal to 1. And also because the angle that we have here is between negative pi over 2 and pi over 2. All that being said, we can now get the answer. Let me plug in this information. The equation of the line is going to be y minus, okay, the y value is pi over 4. That's equal to m, the slope, which is 1/2, and then we have x minus 1. We could leave the line like this. I mean, that is the equation. We could also solve it for y. This is y is equal to, if I distribute the 1/2, I get 1/2 x minus 1/2 plus pi over 4. And we could leave the answer just like this. I mean, either is going to be fine, but this is of the form y equals mx plus b, and there it is. But, you know, where does this thing come from? Why is this the formula for the derivative? Let's check that out next. All right, so to actually prove that the derivative of arctangent is equal to 1 over 1 plus x squared, we need a couple of things first, and we're going to use a trig identity. If you recall, sine squared plus cosine squared of any angle, could be anything, I'll call it theta, it's always equal to 1, and that comes from the direct definition of sine and cosine. What I'm going to do is derive another similar equation to this one by dividing both sides of this equation by cosine squared. So just in case you didn't remember this fundamental identity, it's very easy to derive by dividing both sides by cosine squared. On the left side of my equation, if I divide the cosine squared into sine squared, sine over cosine is tangent, and it is squared, so that is going to be tangent of theta, but it's squared. You would then add on, well, cosine has to divide into this cosine, and they're exactly the same, so you get 1. And on the other side of my equation, 1 over cosine is defined as secant. Again, we have squared, so this is secant squared of theta. So we're going to use this identity in this proof. Here's how the proof works. I'm going to write y is equal to arctangent of x. And note that the thing that we're looking for is y prime. That's what we want to solve for. We want to know, well, what is y prime equal to? I want to solve for that. But there's nothing we can do to take the derivative of this equation. But what we can do is apply tangent to both sides of this equation. So that would be tangent of arctangent of x. The left side is just tangent of y, but the right side, tangent applied to arctangent of x, actually just reduces to x. And that's it. I mean, they are inverse functions, and they should cancel each other. Written this way, well, we can use implicit differentiation to solve for the derivative of y. So I'm not differentiating this equation, I'm differentiating this equivalent one. On the left, I'll start with tangent. The derivative of tangent is secant squared. Again, by the way, that's why I thought about this thing over here. Now back to this. So tangent goes to secant squared of y, but by the chain rule, I have to multiply by y prime. On the other side of my equation, I'm taking the derivative with respect to x, and this x goes to 1. If you want to solve for the derivative, this thing, I want this thing by itself, that's not bad. I can divide secant squared of y to both sides. So the derivative is equal to 1 over secant squared of y. And in terms of implicit differentiation, that's it. That's the answer. I'm noticing that this formula has x's in it instead of y's, so we're just going to do a little bit of work to make this thing look more like this. Okay. I'm going to go over to this identity here. I see secant squared of any angle is equal to 1 plus tangent squared of that angle. So I'm going to replace this with this. I'm going to reverse the direction of it. I'm just going to write y prime is equal to 1 over, okay, and we get 1 plus tangent squared of y. From this step to this step, all I did was I saw a secant squared of an angle. I replaced it with 1 plus tangent squared of that same angle. All right, we're really close. We're almost there. Y prime is equal to 1 over 1 plus, well, tangent squared, maybe I'll write like this. This is tangent of y squared. Same thing, means the same thing. Well, I want this thing in terms of x, and this is what I defined y to be equal to. It's arctangent of x. I'm going to replace this y with arctangent of x. Y prime is equal to 1 over 1 plus, okay, this is tangent of arctangent of x, and that whole thing is squared. Why does this essentially just take us directly to our answer? Well, tangent of arctangent is x, and it's squared, and this remains 1. And here we have our answer. This is a derivation of this formula. It used a couple of things. What does it mean to be arctangent? Well, it's the inverse of tangent. The other thing we used was this identity here. In example 2, I want to get some practice taking derivatives with inverse trigonometric functions. So here at the top, I've listed 6 derivative rules for arcsine, arccosine, and so on. So again, we're just getting some practice. And to start with, I want to take the derivative with respect to x of arctangent of 7x. All right, the way this works is, just to maybe write it so it's a little bit bigger here. I see it's the arctangent function, so I know I want to use this rule here. And it's 1 over 1 plus whatever it is here squared. Since this thing is not just x, but it's 7x, the only difference is that we'll have to use the chain rule when taking the derivative. So the derivative would be 1 over 1 plus, and then it's whatever that thing is squared, which is 7x. But by the chain rule, you have to multiply by the derivative of 7x, which is just 7. And I'm actually going to leave my answer just like this. This is the derivative of arctangent of 7x. Now, what about differentiating something that has inverse sine? So for this, I'll state that, well, you have to know this rule. The derivative of arc sine of x is equal to 1 over the square root of 1 minus x squared. So you'd have to know this. But once you do, you can take the derivative of this function. I'm noting that arcsine and sine inverse are saying the same thing. When I look at this, okay, I see a product of 2 functions, so it's making me think I have to use the product rule, which says, starting with the x cubed, we get a derivative of 3x squared, and then we just copy down the second function, which is this thing. We then add on, okay, leave the first thing alone, but now we have to take the derivative of inverse sine of 2x plus 1. So I'm going to go to this rule to do that. And what I'm noticing is that within the function itself, it's not just x, but it's 2x plus 1. I'll have to use the chain rule. But to start with, you get 1 over the square root of 1 minus Okay, and this is where you get something squared, and it's that whole thing of 2x plus 1. But also, by the chain rule, you have to multiply by the derivative of 2x plus 1, which is 2. So unsimplified, this is the derivative.